Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale computing project of the United States Department of Energy. I'm Mosny Marquez from Lawrence Berkeley Lab. I'll be the host for today's webinar, facilitating electronic structure calculations on GPU-based Exascale platforms. The webinar will be presented by Jean-Luc Fatubert. Jean-Luc is a research scientist in the computational sciences and the engineering division at the Oak Ridge National Laboratory in Tennessee. His expertise is in high-performance computing, where he works at the intersection of material science and chemistry, numerical solvers, and computer science. Jean-Luc obtained his PhD from the Swiss Federal Institute of Technology in Lausanne, in Switzerland, in 1997. Then he went to North Carolina State University as a postdoc, moved to the Center of Applied Scientific Computing at Lawrence Livermore National Laboratory in California, and in 2017 he joined Oak Ridge. We have issued more than 100 tickets for today's webinar. Hopefully, of them show up today. All attendees have been muted upon entry. We'll be receiving questions through the Zoom chat and also Google Doc. I'll paste the address to that doc in the chat momentarily. We asked Jean-Luc to add breaks during his presentation so he can respond to the questions that come in. With that, I'll stop my sharing here. Jean-Luc, take over.
Thank you, Marcus. Thank you, Osni. Here. Okay, you should all be seeing my screen now, full screen. Yeah. Good. Okay, thanks for the introduction, Osni. So I'm going to talk about some work we've been doing under the Exascale computing project. We're part of the CoPA project, which is a co-design center for particle applications, led by Stu Mniewski at LANL. The team includes several people from Los Alamos, where the software that we've been developing originated from, in particular Christian Negre, which is my co-lead on this project. We also have Nick Buck, which is now external, but one of the original members of the team at Los Alamos that developed this software. And we also have one collaborator at Livermore, Daniel Ozekufor. I'm going to start by giving some motivations for our work, and then I'll dive more into details, technical details about our strategy to target Exascale hardware. We're using OpenMP offload and vendor libraries to optimize our performance. And I'll also discuss some solvers we've been developing within this project. And I'll finish with some lessons learned during the past few years. The first motivation, so we are essentially trying to help the community, the electronic structure community, with some libraries that are common to most electronic structure code. And the common bottleneck of many of this code is what we call, computing a single particle density matrix, which is essentially a projector onto the lowest eigenvalues and eigenvectors of an Hamiltonian. So we're trying to provide a library to do that efficiently, that's portable across different hardware, multi-core CPUs, GPUs, and for different matrix formats, dense and sparse, and also distributed formats. By doing that, we give the user the flexibility so that they can use different algorithm and explore algorithm, what works best for them, for what they're interested in, and so for different hardware, and without having to worry about the underlying implementation. Now, one key bottleneck for this code is how to speed up the simulation and trying to enable larger simulation using GPUs. But typically, the time to solution is a limiting factor when you're interested in doing molecular dynamics. You want to solve the problem, the eigenvalue problem of the electronic structure many, many times at every step of a molecular dynamics until you reach a state where you have enough sampling of your system to get the result you are interested in. And so the question is, how long are you willing to wait until you get these results? So we're really trying to work in a strong scaling regime and having a fast time to solution for every step. And it makes it tricky to use the powers of GPU in this case, because as probably many of you know already, GPUs are very powerful, so they can do a lot of operations simultaneously. And to use them efficiently, you need to give them a lot of work. But as you go in the strong scaling limit, you may not have so much work for each GPU. And so it's a balance to find how to use efficiently these GPUs. And so what we're really trying to do, let me grab a pointer, is really lower the time to solution for problem larger than what we can do now. And what I'm showing here also is the complexity of typical solvers. If you take a dense direct diagonalization that's often used in electronic structure code, the scaling goes like the n cube, like the cube of the number of electrons in a simulation. There are methods that scale like the linearly with the number of electrons in the system, but there's some overhead associated with it, and it takes a relatively large system to get advantage of that. And so we're trying to lower the cost of this simulation, both order n and order n cube, to make the simulation feasible for larger systems using GPUs, accelerators. So it's hard to, as I said, a GPU is very powerful and can do a lot of work. Now, if you want to try to use several GPUs simultaneously to speed up this calculation, it's even a harder problem because you need each GPU to have enough work and to even amortize the communication between their work. So you end up with problems that may be too large. If your problem is sufficiently large to fully utilize a GPU, your problem may be too large to do molecular dynamics, and your time to solution may be too long to enable this MD. So this is a difficult task to address. So within the Exascale computing project, we've been trying to help one particular application, which is the EXALT project, also out of Los Alamos, running their atomistic simulation with quantum forces or quantum molecular dynamics. And the way this is used is you essentially launch multiple independent replicas of the system that run MD molecular dynamics with different conditions, different initial conditions or different temperature or different parameters. And on each GPU, you're going to run one single molecular dynamics, one single instance of a molecular dynamics. And the way it's done in this context is by having the ensemble type simulation code parsplice calling lamps, the molecular dynamics code, to run the MD. Then underneath is going to call latte, which is a tight binding code developed at Los Alamos to calculate the atomic forces at the quantum level. And underneath that's where our projects comes in. We're trying to accelerate these codes by developing the tools that this code can use to speed up this calculation. So this include BML, which is a basic matrix library that implements the basic operations we need on matrices, and PROGRESS, which implements solvers to calculate this density matrix. So let me dive a little bit more into what problem exactly we're trying to solve. So when I say we're trying to solve the density matrix, essentially, we need to solve a dense eigenvalue solver typically. So you start from an Hamiltonian that comes from the physical problem. The straightforward way of solving this problem would be to calculate all the eigenvalues and eigenvector of this problem for this Hamiltonian. From these eigenvalues and eigenvectors, you can calculate a projector or a matrix, the density matrix P, which can be computed with the matrix V made of the eigenvectors, and F, which is just a diagonal matrix where the diagonal elements are given by this Fermi-Dirac function, basically a function that takes values 1 for the lowest eigenvalues and 0 for the highest eigenvalues. So this matrix P is symmetric and symmetric with eigenvalues between 0 and 1. In the special case where the eigenvalues you are interested in that correspond to the occupied electronic wave function, and the rest of the spectrum you don't really care about, if you have this gap, this is simply a projector onto the lowest eigenstates. Now, one issue that comes up when you start using GPUs is that not every algorithm works well there. And I'm trying to illustrate this point here by comparing what is the cost of solving a dense eigenvalue problem, which with a standard solver such as the LAPACK DSY-EVD, which is a divide and conquer algorithm for solving a dense eigenvalue problem, and comparing that to the cost of multiplying one matrix with another one. So if you do that on a CPU, your cost for one diagonalization compared to one single matrix multiplication is, less than 10, which is okay. It's a little bit more complicated algorithm. And even though these two algorithms should use a similar number of flops, the ratio is still below 10 and reasonable. When you go on a GPU, the story is different. The ratio, that is the time to solution for solving one dense eigenvalue problem compared to one single matrix multiplication, goes up to as much as 1,000 for matrices that are, like, say, sized 1,000 by 1,000. So doing dense diagonalization on a GPU is not such a great use of a GPU, if you want. It doesn't use the performance of a GPU so well. So it motivates some of the algorithmic development we've been doing. So this is like two specific algorithms we've been focusing on to solve these problems. One for system with a band gap and one for general metallic systems. And these are based on, there are two examples of algorithms based on matrix multiplications only. So the first one, you build an initial guess. Knowing your Hamiltonian, you can do shift and scale this Hamiltonian to give you initial guess. And then you can do a very simple iteration, either taking the square or two times the matrix minus its square, depending on the value of the trace, and iterate this for about 15 iterations until you converge to a very good solution. If you have a metallic system where you don't have a gap between the eigenvalues you're interested in and the rest of the spectrum, but you have a continuous, you have basically a very dense spectrum of eigenvalues near this Fermi level, you can do another algorithm, which is basically trying to represent this function as a Chebyshev polynomial. So, I mean, you can imagine doing the Chebyshev polynomial on single element. You can do the same on matrices. You could, for example, transform your matrix into a diagonal matrix, apply the Chebyshev polynomial to the diagonal elements and then transform back, but you can also do it directly to the matrix. These are actually ideas that were introduced in the 90s and early 2000s with the idea of reducing the cost of the electronic structure calculation for very large systems. going from an n cube scaling to an order n scaling. And the idea behind that was that if you rely simply on matrix multiplication, when you take one sparse matrix, multiply it by another sparse, this is an order n operation. And if you can truncate your result or keep your matrix sparse enough during the algorithm, your overall solver takes order n of operations. Now, this was the original motivation, but what we find out now is that on GPUs, just because the matrix multiplication is so much more efficient than advanced diagonalization, this type of algorithm is also efficient on GPU. And so this is an illustration on the right, where you can see, for example, for a matrix of 1,000 by 1,000, this SP2 algorithm that I showed on the previous slide becomes much faster than advanced diagonalization, much faster than what this is a measurement we did on NVIDIA V100 comparing to the Q-solver to a simple SP2 iteration. And you can see the big gain you can get from using matrix multiplication-based algorithm. Okay, now I'm going to dig deeper into the software we've been developing, and maybe it's time for questions if there are any.
None at this point, so please go ahead.
Okay, thank you. So the two libraries that we've been developing under the umbrella of the Exascale computing project are called BML and PROGRESS. BML stands for Basic Matrix Library, and you can find it on GitHub, open source. This is basically, it implements the basic linear algebra operation that are used in different solvers, from calling advanced diagonalization to matrix multiplication or inversion. PROGRESS, on the other hand, is one level above between this BML and the application code. And that's where we implement the solver, such as this SP2 solver or the Chebyshev that I described earlier. This is also an open source code that you can find on GitHub. Now, when it comes to offloading the code to GPU, one thing we looked into earlier on was to use OpenMP. If you're not familiar with OpenMP, OpenMP is essentially a way of implementing multi-threading in your code with simply adding pragmas in your code. I'm showing in the example on the right. All the black fonts have been used for what you would do on a CPU. And in red, this is the additional things you would do on a GPU to offload. So it includes mapping your data from the CPU to the GPU and mapping the result back to the CPU. So this is available as starting with OpenMP 4.5. And this is the advantage of this approach of using OpenMP is that it's supported by many compilers. You don't need to link with another library, and in principle, it should work on any hardware. Now, in practice, we found some that OpenMP was not sufficient for us to achieve the performance we wanted. So, in particular, for some critical kernels, such as doing a sparse matrix multiplication, simply adding pragmas like this was not giving us a good performance at all. And as we did not expect to see performance change significantly in the near future, what we decided to go for was a hybrid strategy, where basically we use OpenMP offload for things such as memory allocations, data movement between CPU and GPUs, and also non-critical kernels that don't take much time. And on the other hand, to use vendor-specific libraries to do the heavy lifting of the important kernels, such as a sparse matrix multiplication. So this is a summary of our general strategy. So we try to leverage libraries as much as we can, both on the CPU and the GPU. So on the CPU, we just use the standard BLAS, LAPACK, and SCALAPACK. While on the GPU, we try to rely on Magma as much as possible, since it's portable, as well as OpenMP 4.5, but also other libraries that are vendor-specific. Some of the challenges with this approach is that as we're trying to support various GPUs from NVIDIA, AMD, and Intel, it's a lot of, we have to deal with various vendor libraries and interfaces. Indeed, to our knowledge, there's no sparse matrix multiplication in any library that would give us the performance we want and that's portable across all the platforms we're interested in. So the current strategy is to use the best available libraries on the platform we've been working with, such as QSparse and QSolvers and others. And basically what we're doing is doing the work so that others don't need to do it. We basically provide a uniform interface for all these libraries through our library. One of the challenges too is to make OpenMP offload work with these libraries in an environment where the software stack may change, compiler version change, and suddenly something is not compatible anymore, and so on. And this is a summary of our software stack, if you want. So if you have an electronic structure package on top of it, you would call our progress library to solve your problem. And then underneath, you would rely on BML to do the operations. And I'm trying to highlight with the yellow star to show what was new, was introduced recently under the Exascale computing project funding. It includes adding new formats, including a distributed format, and also interfacing with various libraries, distributed libraries, GPU solvers, and so on. Now the matrix formats that we are working with, we have actually 4 formats that we're really supporting, 1 dense and 3 sparse. But for the GPU offload, we've been focusing on 2 on the dense format and 1 sparse format, which is called LPACK. LPACK, if you're not familiar with it, it's basically, it's a format where you decide upfront the maximum number of non-zero values you're going to allow for each row. So if you have a sparse matrix like this one, you're going to say, I'm going to have a maximum of 5 non-zero elements per row, and you store so you can pre-allocate your a big block of memory and store your non-zero values there, and as well as the other information needed to retrieve this data. It has the advantage compared to a standard CSR that you pre-allocate that block of memory in continuous memory. In terms of data types that we're supporting in the code, so we're supporting single and double precision, as well as complex, single and double complex, which is important for many calculations, electronic structure, for periodic systems, in particular, what's so-called K-points calculation that introduce some complex phase. And our strategy is to see code, so we don't have templates available for us. So basically, we're working with macros, and the functions that depend on the specific data types are recompiled with different values for these macros. The Fortran interface is a very important feature for our customers, if you want, for the user codes that are often written in Fortran. So the way we offer this option is with wrappers functions around all the functions that are needed for this application code, or actually for Progress, the Progress library. This is not automatic. This is not done using any fancy tool, but the overhead is pretty low in code writing, as our interface is rather stable and not too many functionality get added. And so this is the approach. In terms of testing and continuous integration, we have a pretty extensive series of tests that runs over all the different data types and matrix formats. This is very convenient also for developers, just as we add options and fix things in the code, make sure everything remains in place. In terms of continuous integration, every pull request is tested on CPU using the GitHub resources. For GPU, we use the resource offered by the OLCF, using Ascent to test the GPU implementation. This is currently done only for the dense format using the Magma implementation. We also use GitHub for issues tracking, our own issues, and as well as users' issues. Okay, now I'm going to go deeper into floating to GPU strategies. It's another good time to see if there are questions.
Yes, Jean-Luc, actually, there. Going back some slides, you mentioned there were you had some problems with OpenMP. And what were those, and the compiler you used? And
so the compiler we use is typically the GNU compilers. We've also used the Excel compiler on IBM, and the Cray compiler on AMD. The main issues have been performance of some kernels, but also making sure it's compatible with the software stack, the libraries, and so on. Everything is compatible. But in terms of the language, in terms of the language, we actually using probably a very small subset of the capabilities of OpenMP. So we've not had any issues of in terms of functionalities that are not well supported or things like that.
So it was mostly compiler issues. Basically, the compiler didn't generate the code as efficiently as you would like it.
Yeah. I will have a performance plot later on showing you how it is the performance we have on AMD.
Okay, and then the compiler. Oh, sorry,
Gabriel. It's better that if we continue and then we delay the questions, wait until then. Thank you.
Okay, shall I continue?
Jean-Luc, please. Yes.
Yeah. Okay. I will actually address some of these questions in the.
Sure. Yes, we'll get there. Gabriel, please bear with us.
Yeah. Okay. So here's a summary of our offloading strategy. So when we talk about dense format, dense matrices on NVIDIA and AMD, we rely essentially on Magma, except for some vendor libraries that are when they are performing much better than the Magma. And one example is a QSolver on NVIDIA that's outperforming the Magma significantly. For Intel, dense and as well as sparse formats on older machines, we're using OpenMP offload for memory allocation, data transfer, and a few other operations, and use vendor libraries for performance critical kernels. The way we use OpenMP, as I mentioned in the questions, we don't use very advanced feature. We use essentially the basic features offered for offloading. One thing we're doing specifically is, so our matrices are objects, if you want to, C struct. And what we do is we don't offload the whole struct, but we offload just the pointers to the data. And this is 3 lines of code that show you briefly what we do, basically allocating the data on the GPU and copying data from the CPU to GPU. So we have a full control of the data movement between CPU and GPU. So as I mentioned, we're using the LPAC format within our libraries, and it's not the same format used by all the vendors. Typically, vendors use a CSR, a true CSR, where the data, each row is stored right after the previous one. And so we end up using functions to convert from one data format to another. One thing we found out too is that some libraries required the columns to be ordered in the right way. We also found issues with workspace required that was so large that we could not really, it was not really useful for us for the wocSPARSE, for example, on NVIDIA. We expect it to be better with the next release. Also, there are some requirements. For example, if you do the matrix multiplication, the AB plus beta C, the sparsity pattern of A, B, and C are expected to be the same one. So these are kind of the issues that we've been facing when trying to use these libraries. Let me now see how we kind of some results and how we did the testing. The first thing is to be able to test systematically for a range of matrix sizes. What we did is we developed our own model Hamiltonian to test performance. There's basically no good benchmark in the field, and we wanted to avoid storing very large matrices. So what we're doing is basically we're using this model, the tight binding Hamiltonian model, which is widely used in the community, with a simple parameterization that allows to mimic different system, metallic system, system corresponding to biomolecules or semiconductors by tuning a few parameters. And we can use that to evaluate performance on these machines. And this is the result we obtained recently on Crusher at OLCF. So, and it shows it illustrates some of the point I was making earlier. So let's look first at the dark blue. This is a performance, so time to solution in milliseconds as a function of the matrix size. And you see this is a performance on CPU using 8 threads. Now, the performance using simply OpenMP, adding simply OpenMP pragmas around our own code give us actually quite a slowdown compared to the CPU performance on AMD. So as you can see here, it's really, it's performed very poorly. So then what we did is, as I was explaining, we started switching the critical kernels with vendor libraries, such as rocSPARSE. And so this is the light blue is the initial implementation. We started using rocSPARSE, and obviously it showed up some, it showed some other bottlenecks that where some of them were, implementation that we've been a bit, not very careful, and things that we didn't think about, and basically after cleaning up the code, we get now a much better performance on GPU using rocSPARSE. Okay, I can pause for another question or two here.
Yeah, there is, we'll get back to the OpenMP discussion later, but there is one here. Can you comment on possible use of features in SQL and any potential impacts on performance?
We have not been looking into SQL at all for now. So yeah, I have no experience with that.
Okay, please continue.
Yeah. So now let me talk about another algorithm. One of the algorithms we have been we're implementing in PROGRESS, which is the Chebyshev solver I mentioned earlier, which is specifically for metallic systems. So, as I mentioned earlier, for metallic systems, the density matrix we're trying to compute is essentially the inverse of this matrix here, with identity plus exponential of that involves the Hamiltonian, shifted Hamiltonian. And basically, this is the eigenvalues of that matrix that we should find. And so basically, we're trying to approximate that function with the Chebyshev polynomial. One problem is if we try to do that directly, is it can involve over 100 terms. And so it becomes computationally costly. You may remember I showed you in one of the first few slides that doing a dense diagonalization can be 100 times or even more costly than a matrix multiplication. But if you need over, more than, a few hundred matrix multiplication, you lose what you could expect to gain from using simpler algorithms. So one trick that we've been using to implement that more efficiently is an old idea by Patterson and Stockmeyer, proposed in the 70s, which is basically to rewrite. I don't expect you to read all this on the right, all the terms, but basically I'm trying to illustrate if you have a polynomial of order km minus 1, that this would be the way you would write it. You can group terms in a smarter way so that you reduce the number of matrix multiplication. So if X is a matrix here, so instead of having km minus 1 matrix multiplication, you have only over the 2 times the square root of that number for multiplication. So if your polynomial order was order of 100, you end up with only 20 matrix multiplication and becomes quite competitive with the diagonalization. So, and this idea was adapted to the Chebyshev scheme, the Chebyshev polynomial for density metric calculation by Ed Gordon's group in Berkeley in 2004. Now, how does it perform in practice? This is a test we did on NVIDIA V100, so on Summit at OLCF. We are comparing what speed up we get from using such an algorithm compared to using a dense diagonalization with the Q solver from the NVIDIA library. And so we're showing here the speed up. And so as you can see, if your matrices are relatively small and your Chebyshev expansion order is not too long, you have a very substantial, a very good speed up. Only if your matrices becomes pretty large. Here is for the black dots are for matrices 4,000 by 4,000, and your expansion and the order of your polynomial extension goes beyond 500. You start being less competitive. So it shows the potential of this type of algorithm on GPUs, in particular for matrices that are not super large. In addition to that, even if you do just matrix multiplication, if your matrices are less than 4,000 by 4,000, or you don't even fill up your GPU with one single operation, a single matrix multiplication. So you could do several concurrently using GPU streams. And so that's one thing we are exploring too. And we're looking at the speed up. So for example, if you think about a simple polynomial of matrices and you want to calculate all the terms up to the power 8. So this is a kind of sequence you can do. And when you have the power of 3 and 4 and beyond, you have several calculations you can do simultaneously. And so you can translate that into GPU streams and have an additional speed up. And so here, depending The upper right figure here shows you the additional speed up you get from using streams as a function of, again, the expansion terms, so the Chebyshev polynomial order, and for different matrix sizes. And again, well, if your matrix size become large, you don't gain so much because one single matrix multiplication, is good enough to keep the GPU very busy. But if your matrices are not that big, you have a pretty good speed up from using this technique. Okay, I can pause for question again, if there are any.
Let me see here. Yeah, it's still related to OpenMP. If you compared OpenMP offload performance across compilers.
We did not here for this project, no. I mean the main one, our main kernel where we were worried about performance. So this is a sparse matrix multiplication was performing so poorly, and we didn't expect a different compiler to do better. This is something we could revisit, but the issues that we were facing there, we didn't expect it to be specific to a compiler, more to the kind of granularity that OpenMP allows us to work with.
And I think related, to this, have you tried the NVIDIA compiler for OpenMP on NVIDIA GPUs?
I don't think we've tried that one. No.
Oh, okay.
No.
So then continue, please.
Yep. Okay. Now, kind of the last technical part. I want to take a few minutes to talk about distributed computation. So even though I motivated the problem, we say we want a very fast time to solution for problems that are not super big, so can do molecular dynamics. We're also interested in somewhat bigger problems, and the question is, how can you distribute across multi-GPUs these larger problems? So there are two approaches that we've been looking at. One essentially is a divide and conquer approach, where you try to divide your matrix into sub-matrices, overlapping sub-matrices, and compute them simultaneously, and then putting the result back together in a smart way. What we've implemented is actually an algorithm that was proposed by Anders Niklason and collaborators at Los Alamos a few years ago. And basically, the main difference compared to the typical approach is that it's the partitioning, the way the fragments are put together is by using the matrix elements. And so basically a graph-based approach where we looked at the strengths of matrix elements between different nodes. And so this way, it provides an automatic way of partitioning a matrix into sub-matrices. And also it gives an order n solver. So basically, for a given partition sizes, you can grow your problem and have a cost that goes only linearly with the size of the problem. And this is some of the results we obtained for this this approach. Basically, what it shows that if your threshold value for the cutoff goes up, basically you're truncating more, you lose your error goes up to. On the other end, if you with tight tolerance, you can have a pretty good accuracy. The other approach is we try to leverage what we did for non-distributed matrix operations. So what we've introduced is a distributed format we call distributed 2D, which is basically essentially it's a wrapper around our shared memory matrices. And so what we end up having is let's say this is a 2 by 2 domain matrix decomposition on 4 processors. Each processor owns a square matrix, which is one of the other formats we're supporting on shared memory. And so this is a very non-intrusive implementation. A lot of the functionalities are essentially wrapper around the shared memory code that we've been working on and optimizing. Some operations have been more demanding, and some we're not even addressing, some are beyond scope. We're not trying to rewrite a new dense distributed solver. For that, for example, we use Scale-Apack on CPU and ELPA on GPU. But again, our library is providing a unified interface for all that. And some operation that we're implementing is, again, we're interested in fast matrix multiplication. So what we're using currently for this format is the kernels algorithm to implement this matrix multiplication. And this is last break. You can take questions before I address the last part.
There are some comments here, and I think we'll have more questions, but let's continue, and then at the end we'll address those.
Yeah, so the last point I want to make is that, so what I've talked about so far is, so you have a dense Hamiltonian, or you have an Hamiltonian, and you try to solve the density matrix as fast as you can using GPUs. Now, there's a whole category of codes. The most well-known is the Planewave code, where it's not that simple. You actually, it's a different use case. You have actually a huge super sparse matrix, and you don't solve it directly. What you do, you introduce an auxiliary subspace that you try to improve iteratively. And in that subspace, you are going to calculate Hamiltonians and density matrices. So this is a kind of the way it looks like. It could, the solution is typically a tall and skinny matrix. The number of columns is a number of electronic wave functions you're computing. And the number of rows is the number of degrees of freedom for each wave function. This number of degrees of freedom could be the number of Fourier coefficients in a plane wave discretization, or the number of mesh points in a finite difference approach. And the ratio between this M and N is very large typically. Now, as I said, you typically don't solve this problem directly in this large space. That could be a mesh of maybe 128 cube or more. What you do, you find a trial subspace in which you're going to improve over time. So this is a tall and skinny matrix that and you're going to project that whole problem onto a much smaller subspace. And what you end up with is essentially the same problem we've been trying to solve with PROGRESS and BML, which is basically now calculating the single particle density matrix within that subspace, solving a linear algebra problem within that subspace, a much smaller problem. Now, if you look at it from a point of view of data distribution on a computer and our main operations, one thing we did a few years ago was try to evaluate this strategy using a proxy app, which is basically, which is essentially an orthogonalization, which we call a Loveday orthogonalization. That essentially what you need, if you have two tall and skinny matrix, you have to take the product between all the columns of these matrices that gives you the gram matrix S. You need to, then you need to accumulate these matrices across MPI task, take the square root inverse of that matrix, and then apply it to a tall and skinny matrix. And now the bottleneck is this, as I'll show you in the next slide, the bottleneck is this calculation, which is basically the same as when you solve this basically solving an eigenvalue problem as is in the whole program. So this is a good proxy app that shows you that utilizes the same operations that rely on the same set of operations. And then what we showed is in practice, so if you have a very tall and scaly matrix and you can distribute, suppose you have as many processors as you want, many GPUs as you want, and you try to strong scale your problem, you end up showing that this square dense diagonalization in this case is a bottleneck more than the communications. We show that on NVIDIA, the communications using the nickel library is actually an order of magnitude faster than this dense diagonalization, even using the type of iterative schemes I've been showing, presenting earlier in this talk. So again, this is really the one of the bottleneck for electronic structure calculation on these supercomputers with GPUs accelerators. So as you should see here, goes up to 96 GPUs, 96 MPI tasks, and yeah, everything else scales very well except for that becomes a bottleneck. Now let me finish with one slide with some lesson learned. Basically, what so it's been an experience for many people, I believe, but using GPUs efficiently is a lot of work. As I showed, using a OpenMP alone is not always sufficient to get a good performance, and maybe I haven't had experience with another code with. I finally got enough performance, but it was really a lot of work. Relying on vendor libraries can help, but this is not easy either. Every library has its own interface, own requirements. Software stacks can be an issue, between compilers and compatibilities and so on. So, yeah, building a software stack that supports all these third-party libraries and multiple GPUs is a challenge. And even if we are towards the end of the ECP funding round, there's still a lot of challenges on this Exascale platform. And finally, one thing that I hope I illustrate with this talk is that sometimes there are algorithms that are more GPU friendly than others and can become more competitive on GPUs than they would be on CPUs, and that can be the one we should use on GPUs. And this is the end of my talk, and I would like to thank you everyone for your attention. And I'll take questions if there are any left.
Yes, thank you, Jean-Luc. There is one here by Victor Yu. Could you comment on the scalability of your distributed matrix multiply on GPUs?
It's not fully optimized at this point because we don't have we've not implemented the GPU-aware communications yet. So I believe this is the bottleneck now, and that needs to be done. Yeah. Again, we are interested in large scale distributed computation, but it's kind of took a backseat with priorities focusing on the single GPU fast time to solution.
And Jean-Luc, in your opinion, Alfred has a question, interesting question. What is the main obstacle to using GPU efficiently?
What is the main, sorry?
Obstacle?
Obstacle?
Yeah.
I mean, it really depends on your application. I mean, can vary. I mean, for us, for example, for the diagonalization, I think, I don't know if you use if you try to do a dense diagonalization with a typical algorithm, I think, for example, we saw that NVIDIA has done a very good job for their dense eigensolver, but even with that, performance is not that great. I mean, I don't expect anybody to be able to do much better. Maybe a totally different algorithm would work. For us, we can use totally different algorithm because we're interested in a specific result, right? When you're interested in this projector, if you want. we're not interested in the individual eigenvalues and eigenvectors. So that's a way we can get around. But if your algorithm, I mean, so one algorithm is one thing. The other thing is, right, we're trying to have portability. So we don't want to rewrite every kernel for every hardware. We don't want to write, in every language. And so relying on OpenMP was a good trade-off for us, but doesn't perform well everywhere. So as I showed, so yeah, it really depends on your application and algorithm.
Gabriel, would you like to unmute and then ask directly to Jean-Luc?
Sure. I only have a comment now. I applaud you for using the libraries. I find that vendors provided libraries always give the best performance. And but then you are stuck with the problem that maybe they're not available on all platforms, right? So who knows what else comes up in hardware, and then maybe they don't have a BLAS implementation, but most likely they will.
Yeah.
And then I think, but because I'm working on the OpenMP committee also, so I'm a defender. And I'm always collecting, missing features from people if they can report some. We really would want to do this and that, but OpenMP didn't allow that. But it looks like for you, it's mostly compiler issues. And I think replacing this whole linear algebra operation with the call to the vendor library, the vendor will most likely have restructured this linear algebra algorithm for you to make it more efficient, to make it perform more efficiently on the GPU. So, and if you would have rewritten it in C, then maybe you could have used the OpenMP directives more efficiently. That's just my comment.
Well, I've heard about OpenMP. We actually have an expert, Jamal, who's on the team, who has been doing some of that work. And I think his conclusion is from knowing the standard and implementations of various compilers that, for the moment, we had, we could not get the performance we expect with OpenMP. In terms of libraries, one thing I would like to add, so as I've shown, one of the main kernel we're interested in is doing a sparse times sparse matrix multiplication. And interestingly, I mean, the sparse times dense is very well used and optimized by many vendors, right? You do a sparse matrix times a vector, or several vectors in a tall and skinny matrix, and this is used by many people, many projects in different contexts. But the sparse times sparse is not as used, and so, for example, I showed you some of the issues we have on NVIDIA, that the workspace is super large and issues like that. And I mean, so just because it's great when we can rely on libraries, and the more used they are by the community, the better they're going to be. And when we get into the area where these libraries are not as used by so many, sometimes they are only lightly tested and may not perform as well as you expect. And so there are, I mean, obviously we are working with vendors and pushing for better solutions, but that's something we discovered along the way too.
Okay, any further questions from the participants? I think we could have perhaps entertained one more. People can unmute if they'd like to do so. If not, thank you very much, Jean-Luc. Thank you all for staying with us.
Bye, everyone.